course. So welcome to my personal meditation room where we'll figure out whether cats are dead or alive or an illusion, whether birds exist, and all those other things. That said, switching over, not to be outdone by Ina and her background, and switching over to this. Here we are, and that's the setup. So I will talk about classical optimization problems now. And before I do that, David is not here, unfortunately, but let me say a few words about what's called class conflict, what is class versus classical. When you look at this, it entertains me that I'm supposed to be classical. When you look at what this means in a dictionary, then you see that classic is used to describe something which is judged to be of very high quality versus classical, which is something referring to the ancient Greek or Romans. So what I'll be telling you about today is really old, like 2,000 years or older. If you look at a different dictionary, classic means high quality. Now that is maybe closer to what we are looking at. Oh, I was too fast here, sorry. Culture of the past to art forms which belong to a long formal tradition. So I think that's something, it's quite funny and interesting that in computer science you're supposed to be something which has a long culture, formal, and so on. So that said, let's look at some of these problems. And when I'm talking about these problems, by the way, I can see some of you in person. That's good because it allows me, so I see Richard and I see Philip and I see the upper half of Bo and Arne and so on. If you actually want to interact with me, you see me in the green screen and I will be able to see and hear what you're saying via the YouTube channel. So Arne is raising his hand.
Could you mute yourself on Zoom?
I will do that.
We hear you twice.
Yes. How's that? Good. That's exactly what the interaction is for. Thank you.
Better.
The upper half of Bo and Arne and so on. If you actually want to interact with me, you see me in the green screen and I will be able to see and hear what you're saying. Okay, as you notice, there's a bit of delay, right? So the YouTube channel and the Zoom has a bit of delay, so that's why I'm taking the moment here. All right, so I'll be telling you a bit about problems, classic, classical, whatever. I would expect that most of you have heard about these problems, and some of you know a lot more about it. But even when you do know what these problems are, there will be some problem instances, some specific examples of problems, and they're numbered, and you're encouraged to actually think about them, look at them, try to solve them manually, not by running a computer or you're starting your quantum computer and so on. So even if you know all these problems, thinking about them, how you solve them is part of this. So it's not so much that I present everything and that's in the books, but I want to make you think about these things. So let's start with something classical that is mentioned even in press releases on quantum computing. So let's go back. And that is a fair number of years ago. Classical in any sense of the word. So we're here in the Mediterranean. I'm talking about a very, very smart person who lived about here. And smart people, that was before the age of Zoom, they needed to travel when they wanted to have an impact. So that was the means of transportation that was used about 3,000 years ago. And this smart person was called for help to solve a really difficult problem over here, which is where he went. And he came up, this seemed to be really, really hard to deal with, really not hard to crack. It took them 10 years and they still couldn't do it because the matters of computation and getting through, whatever, were hard. Eventually, this smart person came up with a very creative solution of putting in a back door and then solve that problem. Of course, you recognize what this is. This was actually some years ago placed on the in the city center of Braunschweig, but of course the original was near Troy. So I'm talking of course about Odysseus. And Odysseus, after he had solved this problem, was on his way back and he dropped off a colleague and then he was almost home. He just needed to turn that corner, but then he got a little side steps. So he sort of made some longer detours. And of course, for those of you who like Greek, you can read the beginning of this. And he got back, all things concerned, that took him 20 years, 10 years spent there, and 10 more years of traveling. So 20 years, which is a pretty good time because that's exactly the time that almost the time that I've spent in Braunschweig. And he came back just in time when his wife at home was under duress. She was besieged by some people and so on. He just came back in time to save her. I mean, that's pretty good timing and all that. And of course, that's something we would like to know. If you start a long-running process, how can you time it that you're there just in time when it needs to be done? It's not clear what she said. It was probably something in Greek, but it may have been something like, couldn't you make it any faster? And when you look at this and you forget about Odysseus, you forget about the Mediterranean, and you look at this path that he traced out, according to legend, then it's very clear that this was not the best route that you could take here. So what is a better way of following this? And that gets us to the first problem, which is the traveling salesman problem. So what you have, and in all our descriptions, we always have an input and an output. Of course, when we will later talk about quantum computers, getting the input and the output, that's a separate challenge. For computer scientists, that's sort of the easier part. So we're given a graph, something like this. We have vertices, we have edges. Each edge has a cost or a length or a time associated with it. And what we want is a cheapest round trip. So something like this, when you look at this and you think of these geometric distances as the cost here, for these 6 points, that's relatively easy. What is the shortest tour that visits all of these vertices and returns to the start? Very classic, and even as you see, classical problem, and it's a difficult problem. Now, just the fact that it's a difficult problem doesn't mean you have to throw up your hands and say, oh well, 20 years is not so bad, or oh well, eventually quantum computers will come and then do everything and come to our rescue, and before that it's just hopeless, so we just guess something, we just do something straightforward, randomized, or greedy, or something else, because just because it's hard doesn't mean you have to do stupid things. Because it's hard may mean that doing clever things and developing new things may give you still a chance. And in fact, here is, so that was the classical world. So here's something in the new world. This is a map, as you easily recognize, that is a map of the continental US. And when we watch closely and look through these colors, you see there's something white lined out here. And what is actually lined out here is a round trip of all the post offices in the US. 13,509 post offices in the US, at least what they were at some point. And it's not just some tour, it is the optimal tour for 13,509 locations. 13,509 is obviously a pretty big number. How often do you need a round trip for that much or even more than that? And also 13,509, how many possible solutions are there? 13,509 factorial. I mean, you could use some symmetry and and bring it back down. But this is a huge number, not just of locations, but of possible tours. So it is somewhat surprising and encouraging that you can actually compute an optimal tour, even for something like this, not using quantum computers, provably optimal. And this was also done, use the 20, something like 20 years again. So David Applegate, Bob Bixby, Vasek Shvatal, and Bill Cook did this in 1998. They won some significant prize for computing in the follow-up. And they also had something else which was somewhat significant, okay, 1998, but they used 10 years of CPU time. So there's that decade of time again. 10 years is not trivial, and 10 years in CPU time is also not trivial. Of course, they did this on multiple computers, and they had all these sorts of protocols and so on and so on. But of course, you know that since then, computers have sped up a fair amount, so every 1.5 years. So that today, that would no longer be 10 years, it would be quite a bit less than that. But still, a few things remain, so this number of possible solutions goes up. Computing power does go up, but even then, there's a lot of mathematics that you can use in the classical setting. And many people are not aware of it, not even in computer science. So this is a significant benchmark when you say like, okay, we can push things in quantum computing, that the methods behind this, which we'll talk about in the future, not today, are not so bad. And of course, the idea is that we combine some of this knowledge and combine some of these methods. All right, couldn't you make it any faster? That is a question you should always ask yourself in these kind of settings, and that comes in two flavors. One is, of course, the question is, can you make it any faster than 10 years? So can you speed up the algorithm? Another question is, can you find a shorter tour? Is that really optimal? So these are two different questions. And of course, not to be too serious here, there's always good cartoons. There's a cartoon, there's an XKCD about everything. So one of the things is, of course, to realize that n factorial is something you can do. Sure, you just try out all possible permutations. You can do something which is called dynamic programming, which is a classical method for increasingly enlarging your set of things you consider and then working your way up from smaller to larger. And that does reduce the complexity from n factorial to n squared, okay, but here's 2 to the n. So that's still exponential, but is not quite as bad as n factorial. So n factorial is basically 2 to the n log n, and now it's only 2 to the n. Okay, better. Now, of course, you can do this in a distributed fashion, and you do it, let things come to you, and then you can do it in constant time. Some people hope and pray and assume, which is futile, that you could replace by eBay by a quantum computer. That's not going to happen. And of course, there's some things about linear programming in the hover text on this, and we'll talk about this as well because that's powerful. So those of you who know what linear programming, cutting planes are, what Cplex does, and of course, we have partners with GAMS on board who are really, really, really knowledgeable about this and make a living on a lot of these things. Now, here are a few questions that are for you. Let's just go here. So here's a little section of the continental US. And let me highlight 10 cities in the continental US. So there's Denver up there in the mountains, and of course that's Chicago, and down here, and so these 10 cities. And what am I doing here? Oh, I'm sorry, I messed up here. Let me do something very quickly on the fly. There we go. Okay, here's the cities, and here is the distance matrix. So for these 10 cities, I give you here the distance matrix, and the way to read it is number 1 is Chicago, and number 2 is Dallas. So if you want to look at the distance from Chicago to Dallas, it's here. It's 92. Actually, it's not 92 because it's 920 miles, but for all intents and purposes, using multiples of 10 is fine. And if you want to get the distance from 2 to 1, it's the same as from 1 to 2, so we can save ourselves some trouble and just have half that matrix. So that's the distance matrix for these 10 cities. And now your mission, if you choose to accept it, is to do these things. And I will not give you the answer today. It's up to you. I will give you these questions. I will send you these. You can look at this. You can look at the numbers. And I want you to take pencil and paper and whatever else. There's the map. So there's some geometric intuition behind it. Do these things. There's 2 different questions, and each comes with an A and a B. The A part, the number 1 part, we just want to find a network that has minimum total length so that you can get from one to the other in a connected fashion somehow. So don't connect everything to everybody else directly, but you can do intermediate steps, but you want one connected network. One connected network that has shortest minimum total length. So just find something and then you get some number, you add up these lengths and you get your solution. Try to find something which is as short as possible and then try to argue that you can't do any better. Alternatively, try to argue some lower bound. So if your lower bound is, if you get a solution of, I don't know, 666, and you find a lower bound of 42, and you say, okay, I can't get this 666, but I can argue that you cannot do better than 42, that is a good answer already. When we try to solve optimization problem, we always need these 2 things. We need a solution, which gives us a value, and we need an argument that we can't do better. Now, ideally, these 2 things match. So here's a solution, and here's an argument why there is no better, why this is optimal. Sometimes there will be a gap between these 2 things. So you may be able to find a solution, and you may not be able to convince yourself that this is the best. So for instance, here, if you have 10 of these cities, you will need 9 edges, so you need some subset of 9 out of these 55 possible edges. That's a fair number of subsets. Maybe you don't want to look at all the subsets, but maybe we can argue, or you can argue, that there is some bound. That is one. That's sort of a warm-up exercise. It's not the traveling salesman problem. It's not finding shortest round trip. That is the second. The second is find a shortest round trip through these cities, any way you want. Now, I have run this before in a smaller circle of colleagues here. Some of you are still here. And of course, what you can do is, I mean, you say 10 factorial. What is 10 factorial? That's like 2 to the 10 to the 4th and so on. So you just enumerate. You can do that, sure, but that doesn't scale. So the question is, can you do something manual where you just try out some things? Find a good solution. That's one thing. So, I mean, you can just draw something and get a good solution. The real challenge, and that is question number 4 here on this slide, is argue that there is a number which nobody can beat, that there is a lower bound. So we try to minimize, and there's a bound that we cannot go through. And that thing needs a mathematical argument that needs some kind of explanation. And we're looking at pen and paper, not because there are no computers, but because the methods that we're looking for, well, eventually will not scale. So if you say, well, but I can enumerate all these solutions, then I say, okay, here's 20 cities. Do you enumerate it then? 20 factorial, it's a bit more. The point is here to give you a feeling for what's involved to deal with an optimization problem, to find a bound, to argue a bound, and maybe find something useful and helpful and appreciate by feeling what it means to deal with a difficult problem. That's the first. Let's keep going. So the second problem, no time for a nap, the second problem, and I've phrased that and put that in an exam situation. So here is classic, whatever, old. Somebody I called Knut Donald. So he's an early computer science student, and he has to pass an exam, something with matrices. I don't know if this is unitary or not. Initially, he has 150 minutes. He needs to look at 20 possible problems. There's a question. Okay, so if you want to ask a question, then you should unmute yourself. Leah was waving at me. Please go ahead. I'm waiting for Leah. Seems we have some lag here in the YouTube and the Zoom. Okay, so if you want to ask a question, then you should unmute yourself.
Yeah, I wanted to ask something. I have never dealt with these kind of problems before, but like when I was seeing the two questions.
Yes, was waving at me.
Yeah, me.
Okay. Please go ahead.
Can you hear me?
Please go.
Or maybe this is the delay now, right? Between
you should look at when you're asking a question. You should look at me in the Zoom.
Okay, I don't know.
Go. Okay, so if you want to ask a question, then you should unmute yourself.
Yeah, I wanted to ask something. I have never dealt with these kind of problems before, but like when I was seeing the two questions.
Yes, was waving at me.
Yeah, me. Okay.
Please go ahead.
Can you hear me?
Please go.
Or maybe this is the delay now, right? Between
you should look at when you ask a question, you should look at me in the Zoom. So
okay, I don't know.
Maybe ask your question in the chat.
Yeah, I wanted to ask something. I have never dealt with these kind of problems before, but when I was seeing the two questions. Can you hear me?
Maybe ask your question in the chat.
Well, can you hear me now through Zoom only?
Can you please mute? Sorry, I think you're causing the feedback, or at least one part of you. Yeah. One of you too.
Yeah, so unfortunately this lag between the two things is a bit of a problem. Let me mute this here and then keep going here. And I need to do this again. And here we go. Yeah, okay. Yeah, the lag apparently has increased. So I will just keep going here. Back here. So this exam is 150 minutes. There's 20 problems. There's 100 points that can be awarded, allocated. And you need 50 points for passing. And the clock is ticking. And of course, then after 30 minutes, 30 minutes can be a really long time, not just 10 years. If it's stressful, then you age by quite a bit. Happy birthday, that was on Monday, turning 84. So after that time, he has 6 points for sure that he knows about, and there's some questions worth 10 points where he has no clue and no idea. So he needs 44 more points to pass to get to these 50 points. And let me show you the remaining points, the remaining things available. And so here's the whole set. You see these are numbered. So there's each triple here is an object that has a number. It has, that's a question, so it will take 20 minutes and will give you 3 points if you do it. And you see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 of these questions. And yeah, so the question here is, what should you do? What should you pick? There are some which take a lot of time, so 40 minutes for 10 points. There are others which only take 8 minutes for 5 points, or just 4 minutes for 4 points. So this one here may be a really good choice, but it's only 4 points. You need 44. So can you pick a subset of these 16 questions which add up to not more than 120 in terms of the minutes? And so you want at least, at most 120 in the second entries of the ones that you pick, and you want at least 44 in the third. And now, for this instance here, that is the question, can he pass that exam? Is there a subset which gives you 44 points in not more than 120 minutes? That is called a knapsack problem. Knapsack, you have a backpack and you have a limited capacity. Now, of course, the capacity of this is 120 minutes. That's the time that you have. And you want to get a subset which is as valuable as possible. Now, you may ask here, if there's not enough lag on Zoom to prevent you from doing that, you may ask here, well, can I just take parts of a question? Is there partial credit? Can I maybe just take half of this question, and this is too long for a few points, but hey, maybe this is not so bad. Can I take a quarter of this, half of that, and so on? So is there partial credit? So that's the next question here. What happens when partial credit is possible? So the two versions of this problem, one is you need to take all or nothing. You need to take it not at all or completely. Or you take bits and pieces of these things. So then you take a fraction, and then you take a fraction of the time, and you get a fraction of the points. In one case, that's called the 0-1 knapsack problem. 0-1, you don't take nothing, you take nothing or everything. And the other is called the fractional knapsack problem, where you can take some bits and pieces. That is the second problem, and I want you to look at these numbers, think about what you want to do here, and come up with an answer whether it's possible or not. Now, mind you, there's a slight difference to that other question before, like the round trip. That was a question of optimality. What's the best? What's the shortest? Here, we just want to satisfy one condition. We want to see if you can get 44 points in 120 minutes. So that's a decision problem. Is there an answer or not? If there is an answer, you can just show it and say, look, add up these numbers, they're not more than 120, and add up those numbers, and they're at least 44. That's a decision which you can say, like, it works. If it is not possible, that may be a little trickier, and we'll illustrate that in a moment in the next problem. Here, similar thing again, and the camera is struggling to keep track of me here. Similar thing again, but of course then you also need to say, like, what fraction do you get? And the interesting question here is, does that result get better? Does it get worse? Does it get better? If so, how much? What's the answer? Can you argue this somehow? What happens? I can give you all sorts of justification and answers to this, but the point is to get you to think and to make you work on this a little bit and figure out what you can do here. Next question. Packing. So knapsack problem means, I mean, from the original meaning, you have a container of 120 and you want to put in some of the parts which are not too expensive, not more than 120, valuable at the same time as much as possible, 44 or more. Now, there may be a situation when what you put in and what it's worth is the same. And then you may ask, like, how much can you put in? Can you put exactly that thing in here? And that gets us to this kind of thing. That's a special case of this knapsack problem. And I will illustrate this in a second, but the input is something like this. You have a bunch of numbers, 7, 3, 4, 5, 6, 7, 8, 9 different numbers. And there's a total sum when you add these up of 240. And the question is, that's a special case of a special case. So the cost and the benefit is always the same. That's this number. And the container that you have is 120, and the complement is 120. So the question is, can you do this? Here you go. So can you take these things, and you see these are, the length here it corresponds to these numbers. There's the 7, there's the 13, there's the 24. Can you split this? Can you split this into 2 sets, each of total sum 120? And when you have one subset which is 120, the total sum is 240, so you know the complement is also 120. So you want to partition this into two things. So can you do this? And here the answer is yes, you can. Let me give you a hint. You saw that, right? Let's just do that very quickly again. Let me wiggle one more time. So you see this when you take these 4, so 53, 7, 31, 29, 7 plus 53 is 60, 31 plus 29 is 60. That's 120, and indeed that works. Here you go. So that's a solution. That is fine. Okay, so verifying this, you can just add up these numbers and you see that's 60 and that's 60, that's 120 and 120. What happens then? I do a slight change here, I do a slight change here, turn that into a 57. So you see, here you go. So I modify this. So I make this a little smaller. I make this a little larger. Now that won't be a solution anymore because that's 124 and 116. Can you still do that? Can you still do that? That's the question. That's the challenge for you here. So that's the thing. What did I do here? Okay, that doesn't work anymore. Maybe I duplicated that slide. Oh well. Here we go. That's the thing. So your challenge here, that's problem number 5, is look at these numbers and with the 20 and the 57 instead of the 24 and the 53 and decide if there is a solution. And if not, try to argue that there is none. If there is one, show it. If there's none, give an answer. Now, one of the things that you will encounter while doing that, of course, that's a manageable size by pen and paper. If you think about doing that by computer for something bigger, then you run into a problem, and that problem is that there's an exponential number of cases. There's an exponential number of possibilities, because for every number, you can either put it in the top or in the bottom in the one subset or the other subset. So I mean the first one, okay, without loss of generality, you put it in one place, but the next one you put top or bottom, and you keep going like that. So there's an exponential number. The number of possible choices doubles with every extra item. So the first one, okay, that's symmetry. So you get 8 more items, then you have 2 to the 8 different cases. 2 to the 8, okay, that's still sort of manageable, 256. But the question is that really inevitable that this is exponentially many cases, or can we save some effort here? Okay, we have another problem here where I will not give you an instance, but I'll show you that problem. That's not a packing cover, but a covering problem. And this is not geometry, this is a graph. So you're given a graph. I give you this graph here. So there's vertices and edges. And what I want, again, your mission is to find a minimum vertex cover, which is a set of vertices of small cardinality, smallest set of vertices, such that all the edges are covered here. So for instance, you could take this one, then this is covered, and that is covered, and that is covered. And you can use that, then this covers this edge, and that, in addition, that is double covered now, and that, and that, and that. And now when you look at this, well, you can check if all the edges are covered. This is covered, that, and this, and this, and this, and this, and this. So all the edges are covered with a total of 5 vertices. That's 5. So similar question that we already asked. This is not going to be an explicit problem for you to work out, because that's not at that level. But can you do it with less than 5? Can you do it with less than 4? Can you give a lower bound on what you need here for this graph? And of course, the general question applies as well. What can you do more generally? So those are, when you count, this is a total of 4 different optimization problems. That gives you a good sample. And they share some properties. And there's a few more things that you can do. Now, let me take a moment for the lag between the YouTube channel and the Zoom to catch up. So wave your hand when you're with me here and comment something there. Okay, Philip is commenting here. And maybe this is a good moment, because that's sort of the very first part where we can go over and maybe address some questions. So Tobias is asking what, and now I will do this. I will unmute myself here on the Zoom so we can make this more interactive. So Tobias is asking, could you maybe say to what industrial problems these could correspond to? And yes, I'd be very glad to do that. The traveling salesman problem, I mean, that's sort of the Drosophila, the fruit fly of combinatorial optimization. And we have in the Cubra proposal, we have some pickup and delivery problems, some routing problems. Those would be generalizations of the traveling salesman problem, where you may have capacity, you may have multiple salesmen that visit multiple locations, but that's sort of underlying to that. We also have some scheduling problems. And when you look at scheduling problems, they typically give you some capacity on some machines and some requirements of making these machines or working on something. And those are typically generalizations of knapsack type problems where you have extra constraints, where you need to make sure maybe that there's extra conditions in what order these things are packed or processed and so on. And vertex cover, you can imagine there's all sorts of things where you need to cover certain conditions or need to carry out certain jobs. You made to, I mean, when you think of geometry, you can place cameras like that. But I think the most important ones are the first ones, any kind of touring and any kind of scheduling, packing, / like that. Now, the one in between, the partition problem, like I said, the partition problem is a special case of the knapsack problem. So we have a bit of a hierarchy between problem versions which are easier or harder. As you will see in the next chapter, this easier or harder is a relative thing. It may not mean that this is really easy, but that's pretty much that. Okay, Tobias is happy with this. Any other questions? So there was a question earlier on by Leah. Yes, please.
Is that working now?
Yes. So on Zoom we're live, right? So.
Yeah, sure. I'm really sorry for the delay before. This is always the thing when you're the first to try to ask something.
Not your fault. Not your fault.
I'm sorry. Okay, so when you had the thing with the cities in the United States, I didn't really get what you were saying with the first question when you were talking about the pairwise thing. I did, because you still said that you have to cover all the cities, right? And so in that sense, I was not really sure in what sense that was different. I think I missed a point there at some point.
No, it's good that you ask. Waving my hands doesn't always explain all the things properly. So in the first, let me just point. Okay, that's I don't have it in the Zoom. So you have a set of locations. Suppose you have, let's just say you have three locations. And there are two different problems. One is to do a round trip. If you have three, that means three edges going in a circle. But if you need to make sure that everybody is connected to somebody, possibly indirectly, then two edges will be enough.
Okay, yeah, right? I get you.
That's the first one. So, and then if I make a more complex thing where you have an X shape, for instance, that would still be feasible. So you have something in the center, and then you have two edges like this. So it's called a connected network.
All right. Yeah, good.
Of course, those people who have seen a few more things, but let me say, this is also called a spanning tree that you want.
All right. Okay, thank you.
Minimum spanning tree.
Good.
Yeah.
Thanks.
And no need to apologize here. I mean, the technology and all this is not your fault. We're trying out these things and not holding back when you have a question. It requires a certain amount of courage. So thank you for not being shy here.
Thank you.
Okay. Any other questions? Now, I do have a bit more. Looking at the clock, we spent a bit of time, so I was thinking of 45 minutes, and I would like a bit of feedback because I can sort of start with the next chapter and see where these things are going. But I would want from you maybe like people in YouTube giving me some feedback here, whether I want to go. Now, while you're thinking about this, I will send around the data for these questions. And what I also want you to think about is how you as a group want to interact. Of course, you can send an email or via that. We can also post things on, there's some Slack and whatever. But that is something where you should let us know. Maybe we'll send you a questionnaire, like how you want to do this. We're just getting started. We have 3 years to do this, but use the time wisely. So as nobody is really speaking up here, let me just single out a person. Tobias, can you give me your feeling, what you want to happen now?
So I don't know how much you've got prepared.
Oh, I can keep going for another hour or two or whatever. That's not a problem. The question is, what would you want me to keep going?
I would have endurance till about 5 p.m. How does that sound? Actually, on Zoom, can you give some reactions? If you just click on the reactions button, thumbs up if you think targeting 5 p.m. would be a good time.
It doesn't have to be 5 p.m.
It doesn't have to be 5 p.m., but maybe less than or equal to
and
5
it's all recorded on YouTube. So there will be a recording of this. There will be a link, and you will be able to look at this. So even if you need to go, and even if you want to skip the boring parts where we're keeping track of this discussion. Okay, so let me keep going. But let me say, before I keep going into the next chapter, which starts here, that here at this point, you should look at these problems. So even if you know your stuff, even if you have seen what it means to do, I don't know, a knapsack problem, you should still look at the data and think about what the outcome is. Because that will give you a physical and emotional relation. It will give you an experience about what it means to solve these problems and what you're dealing with and where you can save some stuff. And it will also give you an appreciation for what I'll show you when I'll show you the answers to these things in the future, in 2 or 3 weeks. And more importantly, later on, when we'll talk about what it means to solve this by computer, you have a better feeling of what the computer does and why some things work and don't, and when we'll talk about some methods for these. So make use of that. That's the point of this. Anyway, taking a deep breath, muting my Zoom, and focusing on the YouTube thing again. So classical algorithms. And here's the thing about complexity. So what we want, ideally, is not solve these problems by hand, but we want a computer to do this for us. And now there may be some difficulties because a problem may not just roll over and say, okay, solve me, but a good problem, a difficult problem fights back. A good problem, a difficult problem makes things difficult. So let's look at what it means to solve a problem, classical problem, by computer, and how we sort of distinguish between problems of difficult classes. So here's the first thing. This is known as the class P. This refers to problems. I'll mention this and elaborate this in a moment. Now, P doesn't stand for perfect, but there's some mnemonics involved where you try to remember what these things mean. Now, so what we want is, there's some properties that we want from an algorithm. So an algorithm that has it all, that does it all, that can do it all and do it nicely, that usually needs 3 properties. 3 properties. It should, for any instance that you throw at it, whether it's 10 points or 13,509 points, or whether it's 8 items or 65,536 items, should, in fast time, compute a best possible solution. So these 3 properties, always fast, optimal. Now here is some specification, a more formal way of stating what fast means in polynomial time. Polynomial time means the length of time it takes as a function of your input size. 8 cities, 10 cities, 13,509 cities, or 8 items, or 256 items. The runtime of your algorithm grows. That's fair because you're increasing the number of things you need to deal with, you're increasing the size of your input, and the extra time it takes longer for a bigger instance. So when you scale up the problem size by a factor of 2, by how much does this go up? And when it's a polynomial, then this means when you double the size of your instance, double the size of your input, then this will go up by some constant, 2 to the k, which is the power of this polynomial. And not just once in a while when you're lucky, but all the time, and not just some solution, but the best. These 3 properties are the ones we care about. And so let's color code this. This is the reliability color of blue, and there's the speed color of red, and there's the quality color of yellow. These 3 things. Now, there's a formal definition, and when you look this up in Wikipedia or some other, then there's P, polynomial time, fundamental complexity class, contains decision problems that can be solved by a deterministic Turing machine using a polynomial amount of computation time or polynomial time. So you can formalize a lot of these things. I will not talk about deterministic Turing machines. This word deterministic maybe is something we're not going to leave things to chance. No rolling dice. God doesn't roll dice in classical computers. But when all is said and done, these are the properties that you want. So here is, when you remember this, the previous slide here that I showed you a few minutes ago, this problem, 0-1 knapsack, is there or is there not an algorithm that has these properties? Can you come up with a general method, and this is what we care about, can you come up with something that you can code one way or another, so that, whether it's 16 objects that each have a time and a point score, an algorithm that deals with this in a time that depends as a polynomial of the size of that problem instance. Now I've been keeping this here deliberately. The algorithm is what we're looking for. The existence of an algorithm. Is there some algorithm? That is a property of the problem. So the algorithm says, yes, there's a good algorithm, or maybe there isn't. So that's a complexity class that looking at problems. And what you will see is that some of these problems, many of these problems, in fact, the ones we care about, are difficult in a very specific way. And there is something here that you can also find here, the Cobham-Edmonds thesis, and Cobham, mathematician, and Jack Edmonds is something that the people in my group know because he's actually my academic grandfather and their academic great-grandfather who came up with this complexity class P as saying these are efficient algorithms. Jack Edmonds called them good algorithms, useful, reasonable algorithms, practically good. Now, of course, there's some discussion about theory and practice. This morning I was discussing some of these aspects, not to that technical part, with a press officer here about why we're hoping that quantum algorithms will be able to do a lot of nice things because, well, the question is, do all these problems, can we come up with good algorithms or not? And if not, what we do then? Let me just turn that into a 2-dimensional graphic. So we have these 3 properties, the reliability, always, the speed, fast, and the quality, optimal. And what you want is an algorithm that combines all these 3 together. Now what you can do is maybe say, well, maybe here's something that I care more about. So maybe I don't care about reliability. I like my risk. I like it fast and furious. So I do something fast, always optimal. So you see that's red and yellow together, but maybe not always. And there's left in, there's some things you can do. These are heuristics where you say, maybe sometimes it works. It's always fast, but always does. You could also say, I'm looking at something which always works, always. And yes, it will compute an optimal solution. So you see combine blue and yellow, but it may not necessarily be always fast. Those are exact algorithms, dynamic programming, branch and bound. When we get to this, especially branch and bound is something where I think we will, in the future, in the course of this project, combining quantum and classical will be good and useful. Okay, here's another thing that you can do where you say, okay, something fast and always, and I replace optimal by good. And then maybe you have approximation algorithms, and there are some examples that you can do. Now, I have seen some of these things even in the quantum algorithms literature, approximation algorithms. An important aspect, just an aside, we'll get to that. It's not an approximation of an algorithm, so it's not approximately an algorithm, so it's only to 50% an algorithm. It may be an algorithm that gives you something which is not too far off an optimal solution. So maybe a tour that is not more than twice the optimal, or maybe when you try to maximize something, gets you, like a knapsack problem, which is a maximization problem, gets you at least half of what you can get, those kind of things. So you have these properties, you have the combination of these properties, and what you would like is something that fits in here, that has the blue, the red, the yellow all together in some brown, golden color of perfection. That's the class P, has all these three properties. And the question is, when you look at this problem 0-1 knapsack, which we care about because it's related to, among other things, scheduling problems, does that belong here? So can you find an algorithm that then has all these three properties so you get an overlap between all that? Or is there some black hole in the center of the landscape here? So here that is. Can you come up with something that does this? Now, when you are looking at this in classical algorithms and so on, but of course you can ask, can you do this with a quantum algorithm maybe, whatever. So, second class, and that is different, NP. Now, I like to, when I introduce that in German, so there's a mnemonic here for this, so check. So somebody gives you a solution, check it, checkable proof. So here's a solution, verify that it works. That is something which you already saw. So for instance, for this partition problem, somebody gives you these numbers, split them into two sets, and yes, it's possible. And whether that is the same or not, I mean, I could talk more about this if you have any questions about this distinction and so on. You should know that this is a huge problem. This is a huge open mathematical problem. The question whether finding a solution in this P landscape or just simply saying, oh, somebody found me a solution, and yes, it is a solution, whether that more or less takes comparable time, that is unclear. Or in other words, of these complexity classes of something that has algorithmically a solution that always in fast time finds an optimal solution, or whether you can just, somebody gives you a solution and you can verify it. Whether this is the same, that is problem number 1 on the list of long-standing open problems which were released once like this was the Millennium Problem, so that was once every 100 years mathematicians do that. And out of these 7 problems, this one is solved, so let's forget about that. But this one here is still open. And the question whether P equals NP, whether constructing a solution or merely verifying it, is comparable in difficulty or not. That is open. So if you are able to answer this, if you're able to come up with this, that's an immediate $1 million, which is more than a Nobel Prize, which probably makes you at least as famous as if you won a Nobel Prize. And people have looked at this. Now what people are thinking about, and I will illustrate that a few slides down the road, is that these are actually different. Now let me give you another problem instance. And this other problem instance is this, to give you a feel for the logic, how some of these problems interact. And I give you this. So this is a knapsack problem, problem number 6. And your mission, if you choose to accept it, is to look at these carefully. Now I will give you a bit more help with that, but look at these again. I will give you these 12 numbers, knapsack. So every item, every number has a cost and a benefit. And here's one really, really nice piece of good news, is the cost equals the benefit. So the question is, out of these 12 numbers, special case of knapsack, can you find a subset which, when summed up, is equal to 111,444. These. So find a subset such that the sum of the numbers in this equals 111,444. Now, there's a few things that you will notice easily. One is you can take them all because the first two are already over 100,000, so that's 200,000 already. But if you don't take them, then the rest is less than that. So let's look at this a bit more carefully. And so let me just put the sum here at the bottom. And let's look at the 100,000 here. Okay, here's the 100,000. And you will notice, in order to get to 100,000 at all, you need to look at these, because that's 10 and that's 10 and that's less and less and less. So to get to 100,000 at all, you need to look at these digits. So when you look at these, we need to pick one or two, the first or the second, but not both. Okay, that takes care of that, one or the other. Let's play that game again. When you look at this, you see there's only these two numbers that have a digit in the 10,000s, which is down here. So look at that. And so if we pick one of those two numbers up here, that will get us to 100,000. But to get to 110,000, we need to pick one of those two. So we need to pick number 3 or number 4, 3 or number 4, but not both, because that would get us to something with 20,000, 120,000, whatever. And we can play this game again and look at this. And when you look at this here, you see those. There's 0, 0, 0, 0, 0. There's a 1 and there's a 1. 1,000 and 1,000. Same game. Pick the number 5 or pick the number 6, but not both. Fair enough. So far, so good. So let's look at this next number, which is a little yellow 4 here. And when we look at these, you see there's a 1, and there's a 1, and there's a 1, and there's a 2, and there's a 1. Okay, but this is a 200, and there's a 100. So these numbers here are a little special. They just take care of this one digit. So when you think about that, you can use them or not. So what is critical to bring these in, you can use this one, you can use that one, you can use both of them. So what you actually need is to have at least, from the ones that you picked above here, you need to be at least at 100. At least 100, and then you can stick in this or that or both of them. So if you're at 200, you just use that. If you're at 300, you just use that. But you need this one, or you need that one, or you need that one. So you need to have this 200, or this 200, or that 200, or two, or all of them. But one of these needs to be taken. So if you write this down, what's happening here, the logic, the structure here, you see that you need to pick this one, or that one, or that one. So that's number 1, number 3, or number 6, right? So that's number 6, number 3, number 1. If you have at least one of them taken, then you can make use of the 7 and the 8 to get this to an even 4, depending on whether you have one of them, or two of them, or even 3 of them. Fine. Okay, next thing here, that 4. Same thing again, when you look up here, there's a 1, there's a 1, there's a 1, and you see that's a 20 and that's a 10, so that's a 2 with no attachments here, that's a 0 and that's a 0. So there's a single 2 and there's a single 1 in this digit. So you need 1 out of those 3, maybe 2, maybe 3, that's fine, but at least 1, because if you don't take any 1, then this is only 30 and you will not get to 40. Same thing again, so you need number 1, number 4, or number 6. And if you take one of those, you can use these two to get to number 4. Okay, one more here. Same thing again, and of course now you know the game. Here's a 1, here's a 1, here's a 1, that's 2, that's 3, that's 5, and there's a 2 and 1 here. So it's in the second spot, in the third, and the fifth. So you need to pick this one, or that one, or that one. Bang. And then you can make this up. Now, what you can do is 2 things. You can convince yourselves that these colored conditions that I wrote down here, they refer to these 6 digits that we have in the 111,444. These are necessary and sufficient conditions, because if you satisfy that condition, you get this. If you satisfy this, you get that. 6. So these conditions here describe necessary and sufficient conditions. What you need to choose here for these 12, from these 12 numbers, to get to an even, precise 111,444. Let's do the second thing. The second thing is we will now translate these conditions here into logic. So logic, bang, here's logic. What this means is we pick number 1, and then when we pick number 1, we pick, say that's a Boolean variable x1, or we don't, and if we don't, we know, okay, we take the second one. So we can write this down as take this, choose that Boolean variable to true or to false, which means you take the second one. Okay, you can do this. You pick this one or that one, you take that one or you don't, in which case you take this one. That gives us a second Boolean variable for this alternative. That's take that one or don't, and then you take this one. That's the alternative. That's a Boolean condition coded by a Boolean variable. Or you do this and you say, okay, well, then I take this one or that one, which means item number 5 or item number 6, which is the third choice I'm making between putting that Boolean variable to 1 or to 0, to true or to false. So that's 3 Boolean choices we have. And now we have 3 more Boolean conditions, because we're saying like, well, you need to pick this one or that one or that one, this or that or that. That corresponds to taking this one, or that one, or that one, which is x1 or x2, or not x3. That's exactly what this logical condition is. So let's write this down. Here you go. That is the logical transcription of this condition on these numbers written in these Boolean variables. So x1 or x2 or not x3. And by the same token, when you look at this, 1, 4, 6, 1 corresponds to x1, 4 corresponds to not x2, and 6 corresponds to not x3. There you go. 1, not x2, not x3. And we have this one here, not x2, not x1, sorry, not x1, or x2, or x3. Not x1, not x1, or x2, or x3. So remember this here, digit-wise, are those 6 conditions. And now I've taken these and translated them equivalently into this logical formula, which means that the logic encoded in this logical formula is exactly what's happening here in these digits, right? So you get this if and only if by these choices, if and only if you can satisfy these conditions, and vice versa. So if you find a solution for this, you will have a solution for that. So let's clean this up a little and look at this. So we need to make these choices. Those are the choices we have. This one, or that one, this one, or that one, this one, or that one. 3 different binary choices, 3 different Boolean variables, 3 different options, 3 times 2 options. And we need to make these choices subject to these conditions. So that is really what we're concerned about. So that is where we make a binary choice, and this is where we have the conditions that we need to satisfy, which is encoded here in these digits. And let me stress this again, this is equivalent. Being able to satisfy that means being able to do this. What does that tell us? Now, problem 6, your mission, of course, is to look at the numbers again and try to figure this out and try to characterize this whole set in hindsight one more time. But I wanted to, the way we're doing these things now, actually do this here in presence. So, specifically, each solution to this corresponds to a solution of this. So that's an encoding not just of the problems but also of these solutions, and vice versa. So if you have something here, you can get something here, and so on and so on. So what you probably want to do is find out what's the full set of solutions. How many solutions are there? Can't be more than 2 by 2, 2 times 2 times 2, so not more than 8, but not all of them work. So how many of these 8 do actually work here and work here? So that's an important step now. If I give you some formula like this, any formula like this, not just this particular one with 3 Boolean variables and some of these choices, any formula of this with n variables and m different expressions like this, which are called clauses, then what we can do is take this and construct a set of numbers like that. Because you see, what we have here is, let me just do that. Here is one of these conditions in yellow. If you squint, you will see that yellow here. And that corresponds to this. I mean, when I start out with this, I can say, well, I stick a 1 in that spot, I stick a 1 in the 3rd spot, and I stick a 1 in the 6th spot. And I generate just two options here with that many digits. So the interesting things happen in this one up here, and this is just filler. This is, some people also call it garbage collection. It's like stuffing material to make this whole thing work. And if you take this one here, you get these numbers. There's a 1 in the first, there's a 1 in the fourth, there's a 1 in the sixth. And of course here, the same thing again. There's a 1 here, come on you 1. And there's a 1 here, and there's a 1 here. So, and that's a big leap. That's going to be, let me just go back one step. Important thing is, if you have some logical formula like that, it's straightforward. It doesn't take a long time to turn that into one of this set of numbers. Basically, this thing, and then you just have this and that. And you say that, and here's something, here's a set of numbers. The important thing is, from here, you can build something like that. Not for every subset sum instance you can do the reverse, because this set of numbers has a special structure. And the way this special structure arose is I took this and I converted into this. Like that, right? What does that mean? And now this is a big leap. If we have, for the numbers, for subset sum, for knapsack, for which subset sum is a special case, if you have a really nice algorithm, an algorithm that's always fast, optimal solution does that, then you can turn that into an algorithm that solves you the decision problem whether you can satisfy these logical conditions. And let me dwell on that a bit more. Can we get some satisfaction? Can we get an algorithm for this satisfiability problem? And that is the problem that we have here, this 3 satisfiability, which looks like this. Oh, I didn't translate that. Oh, wow. Okay, so we have a Boolean formula which consists of some Boolean variables, 1 to n, which may be non-negated or negated, non-negated or negated. And we have a bunch of clauses, which consists of these non-negated or negated Boolean variables, 3 of them. And this is exactly what we had, right? So let me just give you that example. We have 3 variables, x1, x2, x3. And we have, in this case, 3 clauses. That one, that one, and that one. Each one consists of 3 literals. A literal is a non-negated or negated variable. Each one has 3 of them. That's satisfiability. And what we want is satisfaction. What we want is a truth assignment. So an assignment to all these 3, in this case, 3 variables, such that in each of these clauses, at least one is true. This one, that one, maybe more, maybe 2, maybe 3. For this, and for that, and for that. Which is exactly what we were doing on the previous slide. And how hard are these? How hard are these? And now that's a crucial thing. Suppose we have this magic scale, this magic oracle that is able to tell us this instance is solvable or not. For knapsack, here we are. So if you have an instance of knapsack that is able to solve it. Now, over here, that's 3 satisfiability. So suppose we have this magic oracle, this magic scale that says, yes, you can do it, and it will do it in fast time, and it will give it precisely, and it just gives you just the answer that you want. Now here's that problem, 3 satisfiability. So you have one of these logical formulas. And what you just saw on the previous slides is there is a relationship between these, because if somebody says, okay, knapsack, I solved it, here's a perfect algorithm for knapsack, then you say, oh, wonderful, what I care about is this problem, but I can actually take this knapsack instance, here's an example, here's a particular one, and I turn it quick and easy, because I just need to look at these digits like you saw on this previous slide. I just turn that into an instance of knapsack, and it's that set of numbers. Bang. And now this person who claims to have this magic scale, this magic algorithm, this magic oracle that says, well, you can actually do it, or maybe you can't, so just looks at that, just looks at that, and says, okay, yes, you can. And then you can go back and say, I don't really care about this, but hey, he gave me an answer, yes. And you go back and you say, oh, he got an answer here, that means I can get an answer here. Or maybe he didn't, and then there is no answer here. So what you really did is, when you care about this problem, you say, like, this is the problem I care about, this is the instance I care about, you encode it, you do camouflage, you disguise it as one instance, say, like, please do this for me. And when there is an algorithm for this, then you say, ah, okay, that solves this. Now, there are some consequences here. And one means that if somebody has such an algorithm, if somebody has such a pair of magic scales, such an oracle, can do this, can solve it, then you can also use that. Because you don't actually need to come up with an algorithm here. Also, you need just this trivial calculation, like, okay, I just encode that into an instance of that. And then I let him run his algorithm, and then I know this. So if there is a fast, reliable, optimal method for knapsack, then lo and behold, I can do this in polynomial time. That's good. Except that this one here is known to be notoriously difficult. This is a very, very nasty problem. This is the mother of all nasty problems. There was a theorem by Cook from 1972, 50-year anniversary this year, that says if that has a really nice algorithm, then P equals NP. So these classes that I talked about a little earlier coincide. Finding a solution, computing a solution out of nothing is not fundamentally easier, harder, whatever, than just somebody gifts you a solution, somebody has computed a solution, and just verifying, looking and saying, yeah, that does the job. And nobody believes that. So that is not to be expected. So that is unlikely, which is a pretty weak understatement. Which also means, well, that means that if somebody had such a good algorithm here on this side, then this very unexpected thing would happen. And that is bad news, if you want, because you shouldn't expect that such an algorithm exists. But on the other hand, that's also good news, because it means that there's work to be done. And that means that we're in business, and that's basically one of the reasons why these projects exist and why people put their hopes on quantum computers to deal with these difficult problems. These are the ones which are interesting. These are the ones that are difficult. These are the ones that need other methods. Let's look at a bit at the consequences of this. And 3 kinds of service, you will see that in a few minutes, what that means. And let me give you some outcomes here. Algorithms and investment bankers. So what we would want to have are these 3 properties. So always, fast, an optimal solution. Here you go. Now, that's what we would like to have. Now, remember, if you have this, this is called a member of this class P. And we just saw it's unlikely that all these problems, in particular knapsack, has such an algorithm. Having all these three things together. Now, investment bankers are wild and not respected, they make a lot of money, but they also do a lot of bad things. And here's that old story about investment bankers. So a perfect financial advisor should be somebody who, when you ask him for financial advice, gives you honest advice. And of course, that should be smart advice. So that should be somebody who is intelligent. And also somebody who's competent. So maybe somebody who knows this stuff, and investment banker. Now, the thing is, word is that doesn't exist. There is no such thing as an honest, intelligent investment banker, because if you fix two of these properties, if you have somebody honest and intelligent, that's not going to be an investment banker. If you have somebody who's an honest investment banker, that person's not going to be intelligent. And if you have an intelligent investment banker, that's not an honest guy. And so far, so good. But the same thing happens here. You cannot have all three of these properties together for a difficult problem. So if you have NP completeness and financial crisis, then what you have is these three properties of always, fast, optimal solution. That is just having like honest, intelligent investment banker. And the thing is, the intersection of all these combinations of these properties, that is empty. There's what's called the black hole of investment banking. There is no such thing as all these three things together. And the same applies here, because unless P equals NP, you cannot have all these three properties together. And that gets me to the three types of service. So you will sometimes see this sign. It's somewhere, the sign is from the US somewhere. Three kinds of service: good, fast, and cheap. You can pick any two. Good and cheap won't be fast. Good and fast won't be cheap. Fast and cheap won't be good. And you can take that sign and apply it to computing optimization of these difficult problems. And that means we have a problem, we have our work cut out. And when you look at this, of course, there are some ways, and I'll talk about psychology in a moment. At this point, it's not completely settled yet whether P equals NP. So there are two alternative scenarios. One is if P equals NP, which nobody in their right minds believes. There are always some lunatics who think that it's all a big conspiracy of all these computer scientists, and yeah, here's a way of doing P equals NP. Then this whole thing collapses. There's a slight distinction between NP complete, which are the hardest problems in that class, and NP hard is at least as hard as any problem in this class, maybe not belonging to this class as well. But then this whole thing coincides. And that's the scenario which we actually do believe in, which is more likely. There's a subset. So being able to construct a solution is equally hard as verifying. It's at least as hard as verifying it. So there's a subset of this. NP complete are the hardest. This is a subset of this, so that's the intersection of those. So that's when P does not equal NP. There's some things which are not in P, and this is when this whole thing collapses. That is sort of the realistic, and that's sort of the fairy tale, unicorn, nobody believes it scenario. And if you translate that into this landscape again, so for knapsack, that is the realistic scenario. That is where we are. These three things these three properties. We can't have them all, and there's something in between. And of course here, same thing again. That would be the setting, the realistic setting where there's this black hole, which there's nothing. We don't have an intersection in this Venn diagram. And here that's sort of the fairy tale situation where there's the perfection in the middle. And now what people are doing in difficult situations is they try to cope with it. So let me just look at this. There are some profiles. And in these times of pandemics, we've seen that. There's some people who will not accept that this is really true. They will try to argue and plead, not please, but plead. Okay, I wrote please. Plead with fate, argue, and these are lawyers or conspiracy theorists and say, oh, I mean, this whole thing, oh, well, we'll look at this. Or you could trust your luck, it'll be okay. It'll be okay, everything will be fine. Or try to work hard or lower your expectations. This sort of, you can think about that. So, no. It's like, oh yeah, it's gonna be okay. It's like, put your head down and deal with that. Or you say like, okay, well, maybe not everything and deal with that. This can be translated to dealing with this in an algorithmic setting. You have these three properties. The first thing is you can say like, okay, I will not accept NP completeness. Or maybe I have a way to avoid this. Maybe there's special properties. Maybe it's a special case. Maybe there's something else that we can do and avoid this NP completeness altogether. Maybe we're lucky and yeah, there's something magic that happens. Just try to sidestep this whole setting here. Or second option is you say like, okay, maybe not always, but maybe my luck will hold. So I will combine these two properties and I have some heuristic, work fast, and maybe sometimes they work, and maybe I hope and guess and I hope and that works, which is in this setting here, that side. So focus on the red and the yellow, that works sometimes, maybe we're lucky. Okay, next thing, always optimal solution, maybe not hard, combine these two, work hard, and that is something we will do in this project. We will do a lot of hard work, and so keeping an eye on this green option, which means we will compute optimal solutions exactly, but maybe not always fast. Maybe we will spend more time, 10 years of CPU time, 10, 20 years of wandering around the Mediterranean along the way. And of course, there's this way of always fast, but maybe not optimal. That's the purple option. We'll lower the expectation, maybe not optimal, but maybe good. So there's what's called an approximation algorithm, not optimal necessarily, but good within a guaranteed constants of the optimum. So that would be this part of that landscape here, these two. And that's all of this. Personality profiles, compromises, consequences, this. And now, what we agreed on, I have a few more minutes, and let me show you one more thing. I'll do it relatively quickly. I'll give you a chance to look at this and think about it. So what I'll do now is look at this problem. Remember, finding a set of vertices that cover all these edges. Bang, bang, bang. All these edges, here and here. All the edges are covered. And what I'll do now is I will build something. I will build a graph. I have this edge, and I have this edge, and I have this edge. And so you see, in order to cover this edge, I need one of those two. It could be this one, or it could be that one. I need to cover, yeah, let's give this a name, either this one or not this one, then I take this one, okay? You see that has something to do with logic Boolean variables. I take this one, or I take this one, which is another Boolean choice I make. I take this one and that one. And the same thing here, this one or that one, same. And this gives me n vertices. Okay, n vertices. And n vertices from which I can pick. So I pick 3 blue vertices up here, one or this, and I need to do this because I need to cover this or that. So there's a choice. There's 3 choices that I need to make, 3 vertices that I pick up here. Now I'll do something down here where I have a triangle. Now to cover this triangle, I need to cover these 3 edges. I cannot do it with one, but I can do it with these 2, or with these 2, or with those 2. Those are the 3 choices I have. Whatever I choose, 2 out of 3 will cover that triangle. Same thing for that triangle, these 2, or those 2, or those 2. And one more, these 2, or those 2, or those 2. And for good measure, here's a 4th one, these 2, or those 2, or those 2. That gives me 2 for each triangle, so I get a total of 2m of these. That is what I need to do. Those are the choices I do have. That's the full set of choices I do have. And now, just to keep things interesting, I will throw in a few more edges. Here's 3 edges. And I need to cover all these 3 edges. So you see that edge is covered actually from both sides. That edge is covered from here. That edge is not covered. So I should do something here to fix that. I should put this one here over here. And now what you see is I need to actually either pick this one, or this one, or this one, because I need to keep one of these down here uncovered. So the one which is uncovered is this one, or it's this one, or it's that one. So I need to leave this uncovered, or that uncovered, or that uncovered. One of those 3, and regardless of which one, then I can just take the other ones and do that. So what's happening with this triangle is these 3 options, and the same thing here. So I need to, oh, look at that. This is uncovered. So I need to actually cover this one here, or this one, or this one. So if you move this over here, so you see that is covered from here, that's fine. The same thing here, so I have 3 connections, this or that and this, that's that, and this or this or that. And now you see these red edges correspond to what's written here in these 3 logical formulas. And now what you have is Boolean choices up here, x1 or not x1, and so on, and clauses down here, which are encoded in the red stuff. And these triangles mean, yeah, you have 3 different options of satisfying these. Okay, now I'm not giving you extra vertices for that red stuff. That's it. So I'm just giving you, for this graph, I'm giving you 1 for each edge up here, and I'm giving you 2 for each triangle here, and nothing extra. And now what you need to do is allocate the vertices up here and down here so that the red ones are also covered. And that means that you have these variables and these clauses, and what that means is that the logic encoded down here corresponds exactly, the logic in this graph corresponds to logic in this logical formula. And so what you have is exactly that same construction that we already, similar, analog to that construction that we did for the knapsack. So if I give you for vertex cover something, a magic algorithm that solves vertex cover problems, you can take formula like this, translate it into this graph, which according to the previous slide has that structure. And then if you have something like this, which decides if you have a good solution, at most 1 up here, at most 2 for each triangle here, then you can satisfy this. Or if not, then you can or you can't. Which means that this vertex cover problem belongs to this class of NP-hard problems for which we have a hard time of finding a good algorithm where we don't expect there to be a good algorithm. And this construction, what was on the previous slide, looking at the clock, is where I should stop. And that's it for now. That's it for that second chapter, and that gets me to 3 minutes past 5, and that's where I'll stop this and unmute myself on Zoom and give you a chance to talk, and of course we'll follow up here as well. Going over to Zoom.
All right, many thanks, Shandor. I sincerely appreciate the time you took to explain these things to us, and I'm sure on behalf of everyone here, I could say the same. It would be really important at this moment to give us a chance to discuss some of the things we've seen. Are there any questions that people would like to see clarified at this moment? I'm sure have some time to.
Yeah, I could have one little question. So I'm a dilettante on all computational complexity things. So, but it's one thing I want. So, when I've seen in the past all this MP, it has always been formulated in terms of decision problems. So yes, no. So I'm wondering a bit now the connection with the optimality part of your discussion. How does it fit together? Because you somehow made the connection between your. So how does optimality fit in there with your connection to the?
This is a really excellent question, and thank you for that. And let me go back to one of the examples I did, and I will do this in this context. No, let me do this here. Let's go here and forward and back and here. So that will show up in the YouTube in a second. While that is building up, the thing is, this is a decision problem. Is that satisfiable? That is a decision problem. Okay? Now, what you can do, and let me from there switch over to this one here. To this. Okay. So now I'm at the vertex cover. And there's a critical threshold. There's a critical threshold that says, can you do it with at most that many? Can you do it with at most n plus 2m? Or do you need more? So this decision problem, threshold, where is the is that threshold at 2 as n plus 2m, or is it bigger? That problem is NP hard. So that's what this logic says. So now if you could decide this kind of thing, if you say, Is that big enough or not? It is like asking, I'm thinking of a magic number between 1 and 100. Well, make a guess. And then you say, is it 50? And I say, well, it's actually less or more. How many questions of this type do you need to answer? It's a logarithmic number of these questions that you need to answer. So you can do a binary search on the threshold. And you know, binary search is really fast. Logarithm is really fast. So if you had something that tells you, that allows you to make that decision whether it's more or less, then you can optimize by asking a sequence of these questions. So I'm doing a little cheating here when I'm saying, yeah, optimization is hard, because I'm saying like, well, if you can make the decision, if you can answer the decision problem, then you can optimize by just asking a sequence. So I'm being a little informal here, but the formalization is usually on decision problems, but making the transition between deciding and optimizing is pretty straightforward, as you can see, right? This is a really good question, and it's the kind of thing to think about, which is, in this case, when you think about this for a bit, it's not hard to answer, but it is important to ask these kind of questions, because when we get to some other things we'll be looking at in the future, especially when you make the transition from classical to quantum, these kind of things come up and show up. So thinking about this is good and useful. So thanks for that question. Are there other questions? I see some people have shown their faces, start showing their faces on camera, so maybe that's a sign they want to ask a question. Laura is going away, okay, thank you, no question there. Anything else? The important thing, the really, really, really important thing, and more important than decision and optimization, is you should ask yourselves and you should ask each other questions. And I am actually asking you some questions with these problems, and these problems don't come out of the blue. I mean, and also some of these slides are the result from not just doing it here in a couple of hours or so on. This is sort of, there's a lot of history to this. There's a lot of learning and there's a lot of thinking about this. And what I invite you to do is do some of this thinking and do some of this discussion, because what you have in this group here are people who know this stuff and people who don't. But the roles will be flipped when we talk about quantum algorithms and quantum computing. So I invite you not to be shy. Don't just ask me, ask some of these others. We will set this up and we will follow up on this. And of course, Tobias and I and some of the other PIs will make sure that this happens. And that's also what this mailing list is about. So use that, and we'll ask you about your favorite ways of interacting, whether it is Slack or Discord or whatever else. You shouldn't be restricted to just going through some PI on the other side. You see there's 38 people on this Slack, on this Zoom, and plenty of people to go around and plenty of interaction. That said, looking at Tobias, Master of Ceremony.
I have a question about the homework. So you set these problems. What's your expectation? Are they meant to be solved by us by a certain date, or what did you have in mind?
So the plan would be to give you some time to do that. Now, next week we will not be coming together because next week is the kickoff meeting. Maybe Tobias wants to say something about that. But maybe in 2 weeks, we can discuss a bit about where people are. And we would do this starting in Zoom, not on the YouTube, not with delay. And I will send around my slides. I will make them accessible to you so that you also get the particular numbers. Look at them, think about them, work on them. You may not be able to prove each and every single one of them, but think about them, and then in 2 weeks we'll get back to that.
Okay, so the expectation is that we'll have had a look at the problems, and in 2 weeks we'll have a progress update, but
right.
We're not expecting full solutions in 2 weeks.
That's right.
All right. So next week, Shandor mentioned, there won't be a winter school event because we will be having the kickoff meeting for our Kubra consortium, of which some of you here are a member and some of you are not. So basically, if you're part of it, you know you're a part of it, and if you're not, then yeah, we're not meeting at think is the short summary. Is there anything else I should say about that? No. Good. Then I guess we reach somehow a logical conclusion for the meeting for today. Really pleased that you stayed the course. That's still some 24 people, 22 people stayed all the way to the end. That's really an amazing result, and the result and the video is on YouTube, so I'm sure that the people who had to leave will be able to catch up in their own time. What we hope to do is put you in contact with some experts from Shandor's group who will be most happy to discuss with you the problems and the things that you've learned today and answer any questions. And otherwise, I think now's the right moment to thank Shandor again for this fantastic start to the winter school. Before I bid you all farewell, is there anything, any comments that we should discuss now? Organizational points, questions? Hmm?